Hi and hello students, welcome to aptdemy. The topic that we will be learning today is chemical equilibrium, and let us have a look into the subtopics that we will be covering today. The concept of equilibrium, the equilibrium constant, understanding and working with equilibrium constants, heterogeneous equilibria, calculating equilibrium constants, application of equilibrium constants, and finally Le-Chatelier principle. Here are the list of references that one can have a look into for better insight. Now imagine you are crossing a river in a small sailboat, and then there a spring leaks. Okay, so as this leak happens, as the boat slowly fills with water, you look for a way to get out the water from the boat. You find a plastic mug at that point and you start bailing out the water from the boat. After much effort, you are able to lower the level of the water down to a few centimeters, at which point your rate of bailing slows down because you can no longer completely fill the mug by submerging it. So eventually, at this point, the rate at which the water enters the boat through the leak becomes equal to the rate at which you can displace the water by bailing it out. Now, important part. At this point, a state of dynamic equilibrium is reached, where the rates of forward process, what is that process? Water coming into the boat, and the reverse one, water leaving out the boat, these are equal to each other. And the level of the water, because these rates have become equal, the level of the water in the boat will now remain constant. Okay, so this is a very crude way of explaining chemical equilibrium with a real life example. Now we will now learn to express the equilibrium state of a reaction in a quantitative term and study the factors that determine the relative concentrations of reactants and products in the equilibrium mixtures. Okay, so that is what we will be discussing in this lecture. Now here you can see that we have a container, and in that we have a tube, a sealed tube, which is containing frozen dinitrogen tetroxide, which is N2O4. Okay, and this sample is colorless. Now imagine that we are warming the container and the N2O4 becomes a gas, and partially it starts dissociating to another gas which is having a color, and that is brown, and the gas is NO2. So initially it was having, say, only N2O4. Now we have a collection of N2O4, along with that some amount of NO2. Now as the time passes, say if you keep this in the night and let it stay for overnight, and with the passage of time you will see the color changing as we are warming this to a little pale yellow or pale brown color, and then it will form a brown color and the color will no longer change. Now why this is happening? Remember, this is a sealed tube. Okay, so the color stops changing when equilibrium is reached. That means what? Rate of forward reaction of N2O4 gas becoming 2NO2, and the rate of the reverse reaction, which is 2NO2 molecules combining to form N2O4, okay, these become equal. Remember, this is a sealed tube. Okay, so for equilibrium conditions, the container should always be closed or sealed. Now, the equilibrium mixture results because the reaction is reversible. N2O4 can form NO2 and NO2 can form N2O4. This is called dynamic equilibrium, and it is represented by writing the equation for the reaction, in which we are going to use two half arrows pointing in opposite directions, and this would be indicating that N2O4 gas, which is colorless, can form two NO2 gas molecules, which is brown in color, and that forward reaction is indicated by this half arrow pointing from N2O4 to NO2. And in the reverse direction, we can use another half arrow from 2NO2 going to N2O4, representing the process is reversible in nature and it is in dynamic equilibrium. We can analyze this equilibrium using our knowledge of kinetics, that is reaction proceeding with time, the concentration of the reactants and the products, the change, that is kinetics for us. Let us call the decomposition of N2O4 the forward reaction and the formation of N2O4 the reverse reaction. In this case, both forward reaction and the reverse reaction are elementary reactions. So the forward reaction can be written in the following manner, and we will say the rate of forward reaction equals K suffix F, which is the rate constant, times the concentration of N2O4, and the reverse reaction, which is 2NO2 gas molecules combining to form N2O4 gas molecules, and the rate of the reverse reaction, which is R suffix, equals K suffix R times concentration of NO2 raised to the power 2. Okay. So the coefficient over here has to be raised to the power 2 when we are writing the rate for the reverse reaction. At equilibrium, the rate at which NO2 forms in the forward reaction will be equal to the rate at which the reverse reaction is occurring, which leads to the formation of N2O4. Now, what we will do, we will simply say that rate of forward reaction equal to rate of the reverse reaction. So, we will write Kf times the concentration of N2O4 in the forward reaction will be equal to Kr times NO2, that is concentration of NO2 raised to the power 2 in the reverse reaction. And now we can rearrange the equation and write it in the following manner, that is, in the numerator we will write the concentration of NO2 raised to the power 2 above the concentration of N2O4. That would be equal to the rate constant for the forward reaction above the rate constant for the reverse reaction. Now, what we would notice that this constant is actually equal to another constant. Okay, so that is what we are going to discuss now. So as we see that the quotient of the two rate constants is another constant, which, as we will learn, is called now the equilibrium constant. So we see that at equilibrium the ratio of the concentration terms, we can say now, equals to the constant, that is the equilibrium constant. So this concentration terms is now equal to this constant, which is the equilibrium constant. Now, what we can say further, it makes no difference whether we start from N2O4 or from NO2, or even with some mixture of the two at equilibrium. This is very vital point. At a given temperature, the ratio equals a specific value, which is going to be this value. Okay. So if you observed the dissociation of N2O4 at a particular temperature and say that temperature we achieve equilibrium constant, okay, and we take some two mixtures of N2O4 or NO2 and allow them to react with each other and reach equilibrium at that same temperature, equilibrium constant for both the reactions will be the same at that particular temperature. Okay. So now, here we will be discussing a few graphs over here. So once equilibrium is established, the concentrations of N2O4 and NO2 will never change. Okay. So we can see, let us consider the previous reaction in which we were warming N2O4 in a sealed tube. Okay. That is, we had left this tube to stand overnight, and that led to the formation of brown fumes, and eventually we were having the tube containing certain concentration of NO2 and N2O4. Okay, and their concentrations will not be changing after a certain time. The color is not changing. So that was the physical observation. Now let us understand in terms of a graph what is happening over here. So let us consider concentration and time graph. So we have the concentration in the x-axis and time in the concentration in the y-axis and time in the x-axis, and as we can see from initial point, the concentration as the time passes of the NO2 sharply increases, and at the same time we can consider the concentration of N2O4, which also falls with the time. But after a certain point, that point when the color is not changing, the brown color remains the same with time, we will say this is that point, and as we can see, the concentration of N2O4 is no longer changing, the concentration of NO2 is no longer changing. So this point we will say equilibrium has been achieved, concentrations of both these molecules stop changing after this point. Okay, let us now consider rate versus time graph. Rate is along the y-axis, time is along the x-axis. Now the rate at which the forward reaction is happening, that is shown over here. You can see there is with time the rate of formation of NO2 is increasing. Okay, and similarly the rate of decomposition of the N2O4 is decreasing with time, but after a certain point, at that point, like I've said over here, the brown color is reached and that brown color no longer changes. Okay, we will say system has achieved equilibrium. Okay, at this point, the rate of formation of in the forward reaction N2O4 two molecules of NO2, and the rate of backward reaction, that is the combination of two NO2 molecules to N2O4, these rates are equal to each other. Okay. So what lessons have we learned from this previous slides? Okay. The first one, at equilibrium, the concentration of the reactants and products no longer change with time. For equilibrium to occur, neither reactants nor products can escape from system. That is why it is called a closed system, or a sealed tube is always used. At equilibrium, a particular ratio of concentration terms equals a constant. Okay, and that constant will be having a specific value for a particular temperature. So now the equilibrium constants, and we are going to discuss over here a very important equation, that is the combination of nitrogen gas, okay, with hydrogen leading to the formation of ammonia. Now here you can see from the reaction itself, 1 mole of N2 gas combines with 3 moles of H2, okay, and it forms 2 moles of ammonia. Now this reaction is the basis for the famous process known as the Haber process, which is critical for the production of fertilizers and therefore critical to the world's food supply. In Haber process, as I have mentioned, nitrogen and hydrogen react at a high pressure and high temperature in presence of a catalyst, which is molybdenum and iron, to form ammonia. Okay. So how do the concentrations of H2 and N2 and NH3 vary with the time is now shown over here in the graph. Now notice that an equilibrium mixture is obtained regardless of whether we begin with N2 and H2 or with NH3. Both the cases, the equilibrium condition will be reached from either direction. So here in this case, we are starting only with reactants. So for that we have a graph. So as we see, with time, the concentration of hydrogen, which is the green line, and the concentration of N2, they are falling, and after a certain point, the concentration for both of these gas molecules never change. The orange line is indicating the concentration of NH3 that would be increasing with time, okay, and after a certain point it will not be changing. So this dotted line, after which the concentrations for these three molecules is not changing, is known as the equilibrium, or we will say this is the point where equilibrium has been achieved. Okay. Now in terms of concentration, you can see at the very initial point there is zero concentration of ammonia, but the concentration of N2 and H3, if you compare, then they will be in a 1:3 ratio. Okay. Now again we are considering the reverse direction where we are starting with the NH3. Okay. So the NH3 will be having highest concentration among all the gas molecules when we start the reaction, and with passage of time, as we can see the orange line, the curve is dipping, and after a certain point it becomes horizontal with the x-axis, and so also with the blue line and green line representing nitrogen and hydrogen concentration, hydrogen gas concentration. So over here, with passage of time, the curve will be increasing, okay, again maintaining a ratio of 1:3, and after a certain point, that is the equilibrium point, the lines become horizontal, the lines become parallel to the x-axis. Okay, that is a better way of saying it. And that would be indicating that the concentrations with passage of time after this dotted line, which is the equilibrium point, okay, is not changing. Okay. So now Maximilian Goldberg and Peter Wage postulated their law of mass action, which expresses for any reaction the relation between the concentrations of reactant and products represent at equilibrium. So suppose we have a general equation, equilibrium equation, wherein we can see A moles of A plus B moles of B combine to form D moles of D and E moles of E, where A, B, D and E are the chemical species involved, and A, that is a, small b, small d and small e, or the lowercase a, b, d and e are the coefficients in the balanced chemical equation. According to the law of mass action, the equilibrium condition is described by the expression. What is that expression? So we are writing Kc, K suffix C means concentration, okay. So we will write concentration of D raised to the power D, concentration of E raised to the power E, that will be the product's concentration, and those will be in the numerator. The reactant concentration will be in the denominator. So this above the concentration of A raised to the power A, concentration of B raised to the power B, this relationship is called equilibrium constant expression. Now this subscript C, what is the meaning of it? As I told, it indicates concentration expressed in molarity, okay, are used to evaluate the constant. Now The numerator of the equilibrium constant expression, as I have told you, is the product concentrations of all the substances on the product side of the equilibrium equation, and each are raised to the power equal to the coefficient in the balanced equation. This is already discussed. The denominator is similarly derived from the reactant side of the equilibrium equation. Now we will write the equilibrium constant expression for the Haber process. So what we will write, we know the equation was 1 mole of N2 combining with 3 moles of hydrogen and forming 2 moles of ammonia. So if you are using concentration terms relating to molarity, we will say NH3 raised to the power 2, because 2 was the coefficient before NH3. Then above in the denominator we will be having concentration of N2 raised to the power 1. So for 1 we don't write anything, it is pretty understood, that is 1, and concentration of hydrogen raised to the power 3, because 3 moles of H2 are involved. Okay, so now we will extend this idea, writing equilibrium constant expressions. Illustration 1, write the equilibrium expression for Kc for the following reactions. So we have been given part A, B, C. Okay, let us solve. So these are the products and these are the reactants. So we will say for A, Kc would be concentration of oxygen raised to the power 3 divided by concentration of ozone raised to the power 2. For B, we would write Kc concentration of NaCl, which is the product, raised to the power 2 divided by concentration of the reactant NO raised to the power 2 divided by, multiplied by, that is concentration of NO raised to the power 2 multiplied with concentration of Cl2, which is raised to the power 1. I will not write that, as I have already discussed. Now, so yeah, that was the solution. Have a look at it. So now we have in the next, so for this we will write Kc concentration of the complex Ag NH3 whole twice, so this is twice, plus above Ag plus ion concentration times the concentration of NH3 raised to the power 2. So this is how we will be solving these problems. Evaluating Kc. Illustration 2. Evaluate the value of Kc for the reaction N2O4 gas going to 2NO2 gas if the equilibrium concentrations of the reactant and the products are given. That is, the concentration of N2O4 equals to 0.00140 molar and that of NO2 is 0.0172 molar. So for the above reaction we have to calculate Kc. So we will write NO2 raised to the power 2 divided by concentration of N2O4, and let us plug in the values, that is 0.0172 okay, raised to the power 2 divided by 0.00140. So now if you calculate this, the answer that we will be getting is going to be 0.211. That will be the value of Kc. Now what we can understand from this table, we have started with different concentrations. Okay, we have conducted various experiments with this N2O4 and it is forming 2NO2, temperature being maintained at 100 degrees centigrade. Okay, so we have the initial concentrations, okay, taken, and then according to that we are getting different concentrations of N2O4 and NO2 at equilibrium. But if we involve these concentrations and we keep calculating the Kc values, we see the Kc values differ by a very slight amount. Okay, they are almost equal. That means we come to a very important conclusion. And what is the conclusion? The value of Kc does not depend on the starting concentrations of NO2 and N2O4. So even though we are having different concentrations of NO2 or N2O4, okay, the equilibrium constant will never change. Equilibrium constant in terms of pressure, it is known as Kp. So when the reactant and products are gases in a chemical reaction, we can formulate the equilibrium constant expression in terms of partial pressure. So when partial pressure is expressed in atmospheres are used in the expression, we denote the equilibrium constant Kp, where P stands for the pressure. So again we have taken the equation A moles of A combining with B moles of B, okay, forming D moles of D and E moles of E. Okay, so if we want to write the equilibrium constant in terms of pressure, so we will write Kp equals partial pressure of gas D raised to the power D times partial pressure of gas E raised to the power E above partial pressure of gas A, which is in the reactant side, raised to the power A times partial pressure of gas B raised to the power B. Okay, where Pa is the partial pressure of A in atmospheres, Pb is the partial pressure of B in atmospheres, and so forth. Now we also know from our ideal gas equation that Pv equals to nRT, or we can write P equals to N above V times RT. So now what will be the expression for partial pressure of gas A? We will write Pa equals Na by V and that multiplied with RT. Now Na by V can be written as the concentration of gas A expressed in molarity. So what we will do for all the partial pressures, okay, we will be now writing them in this format, and as we do, we can see Kp now will be equal to, within parentheses, we can write concentration of D times RT, the whole thing raised to power D, and for the E gas we can write within parentheses concentration of E times RT and that whole thing raised to the power E, and the similar thing can be written for the reactants. Now what we are going to do, we are going to segregate the concentration terms and we will write them within parentheses, and the RT that is lying above, that is in the numerator, and the ones in the denominator will be written in this format. And as we know, D plus E minus A plus B is basically number of moles of the products minus number of moles of the reactants, and that is nothing but delta N. Okay, so now this one is actually Kc. So we'll write Kp equals Kc RT, and as I have told, D plus E within parenthesis minus A plus B within parenthesis is actually equal to the difference in the number of moles of the products and reactants. So that is written as delta N. So now Kp can be written as equal to Kc within parenthesis RT to the power delta N. So now we will do an illustration in which we are going to be converting Kc and Kp. Illustration 3, for the Haber process, N2 gas combining with H2 forming NH3. The Kc value given to us is 9.6 at 300 degree centigrade. Calculate Kp for this reaction at this temperature. So how do we solve this problem? First of all, we will calculate delta N. Okay. So even before that, let us write the expression. We know Kp is Kc times within parenthesis RT raised to the power delta N. Okay. So let us find delta N. So delta N is number of moles of products minus number of moles of reactant, and that we can see it is 2 minus 3 plus 1 for ammonia, 3 for hydrogen. So this is coming to be as minus 2. So now we will write Kp equals Kc RT minus 2, or we can write Kc by RT to the power 2, or now we know the R that we will be using over here is going to be 0.082. Since we are calculating Kp, so it should be in atmosphere, liter atmosphere per Kelvin per mole. Okay, so Kc given to us is 9.6 divided by 0.082 times temperature needs to be converted to Kelvin. Okay, so it will be 573, the whole thing squared. Okay, and the answer from this that we will get is going to be 4.34 times 10 to the power minus 3. Okay, so this is how we need to solve such problems. Equilibrium constant and units. The activity of any substance in an ideal mixture is the ratio of the concentration or the pressure of the substance either to a reference of concentration or to the, that is in molarity, or to a reference pressure 1 atm. Okay, so for pure solids, important again, and pure liquids, the situation is even simpler because the activity is then merely equals to 1, again with no units. Illustration 4, what is it about? If the concentration of N2O4 in an equilibrium mixture is 0.00140 molar, what is the activity? So this value has to be in reference with concentration 1 molar. So we will say activity will be 0.0014 molar, 1 molar, that is equal to 0.00140. Okay, that is what we will write. Understanding and working with equilibrium constants. The magnitude of the equilibrium of an equilibrium constant can tell us about the relative concentrations of reactants and products in an equilibrium mixture. So when K is very large than 1, equilibrium lies to the right hand direction, that is there will be more amount of products and less amount of reactants in the equilibrium mixture. When K is very less than 1, we will see equilibrium rise towards the left hand side of the reaction, and there will be large amount of reactants and very less amount of products. So the question is, what would this figure look like for a reaction in which K is almost equal to 1? So from that we can think that the boxes for the reactant and the box for the product they are going to be very much similar. So if this is for the reactant and we will say this is for product, okay, both will be of same size. Okay, interpreting the magnitude of an equilibrium constant, illustration 5. Okay, the following diagrams represent 3 systems at equilibrium, all in the same size containers. A part of the problem is, without doing any calculation, rank the systems in order of increasing Kc. Okay, so we have to find which of these boxes have greater number of products, okay, than the reactants. So let us do the first problem. So if you are taking box number 1 and 2 and 3, as we can see, the reactant here is blue and the product is red. So if we are counting these, we will see 1, 2, 3, 4, 5, 6, 7 and 8. 8 such red spheres are there, and those are the products, whereas the blue spheres are the reactants. So it is 8 products and 2 reactants in the equilibrium mixture. What about box number 1? Now over here we are having the blue spheres representing products. So there are 1, 2, 3, 4, 5, 6 products, and 1, 2, 3, 4 reactants. So for both of these, the Ka value will be greater than 1. Okay, but it will be higher or highest for box 3. Okay, if we are just comparing box 3 and 1. So over here, since they have already asked us to do no calculation, but just rank the systems in the increasing order of Kc. So Kc for, Kc for box 3 will be highest, followed by 1, and as we can see, we are left with only option 2, and in that we can see there are only 1 product molecules, and the rest of the molecules are, which are green in color, are the reactants, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, I think, yeah, the counting is correct. So there are 9 reactants. So over here we will say this will be having Kc less than 1 and will be the lowest. So this should be the correct order for Kc. Now this is the part A of the problem. Part B of the problem, what does it say? If volume of the containers is 1 liter and each sphere represents 0.1 mole, calculate Kc. Okay, so mole by concentration obviously is mole by volume is a concentration. So over here 0.1 divided by 1 will be obviously 0.1 mole per liter. Okay, that is molar basically. So let us consider number 3 first. So in number 3, what is the value of Kc? So for 3, the value of Kc will be number of product. Over here is, I believe, 8. Yes, it is 8. So it is 8 times 0.1 divided by 2 times 0.1, and the value that we will get is 4. Okay, what about 2? So let's say Kc, and that would be 1 times 0.1, and that is 9 times 0.1, and the value that we should be getting is 0.11. What about 1? Here the Kc, we will say it's basically 6 product and 4 reactant molecules. So that is 6 times 0.1 divided by 4 times 0.1, and the value that we will be getting is 1.5. So this is how we need to calculate the Kc values for the part B of the question. Okay. Now, okay, so relating chemical equation, stoichiometry and equilibrium constants. Now there are many ways to write a balanced equation for a given reaction. For example, if we multiply equation below by 2. So this is the equation which is basically N2O4 gas going to 2NO2 gas. Now suppose we multiply this equation, so the new equation that we will be generating is going to be 2N2O4 gas, and that will be forming 4NO2. Therefore, the equilibrium constant expression for this new equation is, suppose we are writing this as to be Kc equals concentration of NO2 raised to the power 4 above the concentration of N2O4 raised to the power 2. Okay, so now the concentrations of substances in the equilibrium mixture will be the same no matter how we write the chemical equation, either this way or that way. But the value of Kc, important point, that we calculate would depend on how we write the equation. Okay, so let us understand what we are trying to say over here. So now for this, let us write the Kc as Kc prime, and that would be, we will say, NO2 gas concentration raised to the power 2 above concentration of N2O4 raised to the power 1. So if we try to relate now Kc prime with Kc, we will say Kc will be equal to Kc prime square. Okay, so let's say Kc has a value, Kc prime has a value x. Okay, so this equilibrium constant for this equation is x. Okay, then what will be the value for this equation? So for that we know Kc is equal to Kc prime square, so we will say x is square. So depending on how we are writing the equation, what are the stoichiometric coefficients before the molecules in a balanced equation, the value of Kc will change. Okay. It is also possible to calculate the equilibrium constant for a reaction if we know the equilibrium constant for other reactions, and then we will do what? We will add up to give us one we want. For example, let us consider the following two equations over here, and their equilibrium constant expressions are written as follows. Okay. And that is at a temperature of 100 degrees centigrade. So now the first equation is what? 2NOBr gas, reversible arrow, and gives us 2NO gas plus a Br2 gas. So while we are writing the expression for the equilibrium constant, we will say concentration of NO raised to the power 2, because the coefficient over is 2, times concentration of Br2 above the reactant is NOBr, so it will be concentration of NOBr raised to the power 2, and let's say that value for Kc1 is 0.014. Okay, now we have another reaction, say it is 2. So for that, Br2 gas is combining with Cl2 gas, forming an interhalogen, and that to 2 moles of BrCl, and then again the equilibrium constant expression for this one or this reaction will be product concentration above reactant concentration. So it will be BrCl raised to the power 2. The reactants are Br2 and Cl2. So that will be concentration of Br2 times concentration of Cl2. Okay. Below the concentration of BrCl raised to the power 2. And let's say the value is 7.2. Okay. Now, if we add these two equations, the common factors will cancel out. Okay. So here, if we add, so here Br2 and Br2 will get cancelled. Right, and what we are left with then, we would say we will be left with, in a third new equation obtained by adding equation 1 and 2, we will say 2NOBr gas plus Cl2 gas, reversible arrow, and that is going to give us 2NO plus 2BrCl gas. So let us write the equilibrium constant expression for equation number 3, and so over here these are the products and these are the reactants. So we will say concentration of NO raised to the power 2 multiplied with the concentration of BrCl again raised to the power 2, as the coefficients before these two are 2, and then that is above, or we can say divided by, concentration of NOBr raised to the power 2 multiplied with the concentration of chlorine whose coefficient is 1. Okay. Now if we just separate these in a manner, okay, by, so for this we will be multiplying this numerator and denominator by the concentration of Br2. So the new equations we will be having is going to be concentration of NO raised to the power 2 times concentration of Br2 divided by concentration of NOBr raised to the power 2, and this is what? This is very similar to this. So we can write this to be as Kc1, and this one is very similar to Kc2. So we can now say the new equation that we obtained by adding these two equations for the equilibrium constants, okay, when we add two such equations, okay, the third equation obtained, the third equation that we obtained, if we write the equilibrium constant expression, so we will say the new equilibrium constant expression will be just the product of the equilibrium constant of equation 1 and 2. And so from that we can calculate the value of equilibrium constant expression, and we find that it is going to be 0.1.